Good afternoon, everyone. It gives me immense pleasure to welcome you all to today's Brahmagupta Physics Colloquium delivered by Professor John Morton. He is the professor of nanoelectronics and nanophotonics at University College London, with research interests in spin-based quantum technologies, including quantum computing and quantum sensing across a wide range of materials and devices. After reading electrical engineering at the University of Cambridge, he undertook a PhD position at University of Oxford, where he worked on controlling spins as quantum bits, developing techniques for it. And John was a Royal Society University Research Fellow from 2008 to 2016. He has held consecutive European Research Council grants. In 2012, he moved from Oxford to UCL, where he is director of UCL's Quantum Science and Technology Institute. And since 2025, he is the principal investigator of the UK Research Hub on quantum biomedical sensors. John is also a co-founder of two successful quantum computing companies, Quantum Motion, which develops silicon-based quantum hardware for computation, and Phasecraft, which develops quantum algorithms. And they have a combined workforce of around 100 researchers. His awards include Nicholas Kurti European Science Prize, the Institute of Physics Moseley Medal in Experimental Physics, and the Sackler International Prize in Physical Sciences.
Thank you very much. Well, what an immense pleasure it is to be here. Thank you very much for the invitation. My first visit to India, and I couldn't have wished for a warmer start and a warmer welcome from the faculty here. So, I'm going to be giving a presentation which is focused on very much a traditional physics topic in quantum computing, but looking at how the tools of the electronics and semiconductor industry can really help to drive that research forward. So, does anyone know what this is? Who said the ENIAC? It is not the ENIAC. I have given this talk in the room or the building where the ENIAC was first built in Philadelphia. This is the Colossus, the UK version. Predated it. It was the first programmable electronic computer. And where was it built? Does anyone know? Also a popular myth, it was first built in London at the Post Office research station. And I took this photo. This is a view from near my house in North London. It's the building where Tommy Flowers first built a machine out of valves that the people in Bletchley Park said was impossible to build. And after he built it there, then they took it over to Bletchley Park where it became famous. So this was, as I said, the world's first electronic programmable computer, but it's not what we think about when we think about computing today. When you think about computers today, this, right, which is, of course, silicon. It's become synonymous. We talk about Silicon Valley and the Silicon Age, and it's because of the power of the silicon integrated circuit. First born in 1960 when there were 4 transistors integrated on a single piece of silicon, then the first commercial microprocessor with a couple of thousand, and then now tens of billions of transistors integrated on a single chip. So nothing can stand in the way of the dominance of silicon in the information industry, surely. Well, until this paper came along. 1985, a paper by David Deutsch, talking about quantum theory, the Church-Turing principle, and the universal quantum computer. And he was arguing that it is possible to build, that there's what we thought about as a general purpose computer, the Turing machine, was actually just a limited example of computing, that there was a more general form of computing. And actually, he is in many ways a philosopher. He wanted to build this machine in order to prove the multiverse theory. And his reason for building quantum computers is that classical physics is false, and so we should stop trying to build computers based on classical physics, but use quantum physics instead. So this is already, to understand this, we need to think about the importance of the physical resource that we use to store information. And when we think about computing, at least, that physical resource has transformed over the years and decades. The mechanical engine from Babbage used as its physical resource about 10 to the 20 atoms in terms of the position of a gear. When we moved to vacuum tubes, a bit of information was about 10 to the 9 electrons. With the first integrated circuit, it was about 10 to the 7. And computers today are using of order 1,000 electrons to distinguish between a 0 and a 1. Why is that important? It's because information, I'll skip this, information is physical. So where we encode the information changes the nature of the information itself. If, instead of using thousands of electrons or atoms to store the information, we encode this information within quantum systems. For example, we take a single photon and we can split it in one of two different parts using a beam splitter. We call one part a 0, one part a 1. Or if we use different atomic orbitals of an atom, or if we choose the orientation of a spin, or the direction of current in a superconducting loop, if we choose these units of information as our 0 and 1, then because they're quantum states, then it's also necessarily possible that you can have a superposition of these states. So because quantum mechanics, Schrödinger's equation is linear and we can have superposition, then encoding even the most basic unit of information, a binary digit, within a quantum systems enforces a richer type of information, which is the quantum bit. So instead of being limited to 0 and 1, we have this richer state. It can be a superposition. Of course, you can have any amplitude, any balance of superpositions, or a phase. And so, whereas for 64 bits, we only need 64 bits to represent that number, and we can think about one qubit as a point on the surface of a sphere. If we had 64 qubits, of course, there's no way to show this graphically, but to describe it, I would need 2 to the 64 numbers. So simply to write down and monitor the evolution of a 64 qubit machine, I would need not 64 bits, but 10 million terabytes. So this kind of highlights the potential computational power of quantum information compared to classical information. Feynman is famous for saying there's plenty of room at the bottom. That's, in many ways, what's driven the shrinking down of these sort of transistors to store information at small scales. But as Galton Cave said, there's plenty more room in Hilbert space, in this exponentially expanding computational space that quantum bits can occupy. So what could these computers do? Well, in one level, it is, as Deutsch said, the most general form of computing that the laws of physics currently allow. That's one good reason to build them. But Feynman identified already the potential to simulate nature, because nature is quantum mechanical, so if you want to simulate it, you need a quantum computer. And he also said, by golly, it's a wonderful problem because it doesn't look so easy. He was definitely right about that, I can say, after spending more than 20 years trying to get somewhere with this. So looking at making more accurate models of materials, molecules, drugs, using these quantum computers. And if you want some examples of work that's been done in this area, have a look at this materials modeling database from Phasecraft that shows the computational requirements for modeling different materials like battery cathode materials. And it's not just simulating nature. Other problems like optimization problems can be accelerated using quantum computers. And here's an example on how energy grid usage can be optimized, saving, at least for the UK, potentially billions through optimal grid management. So the other interesting thing, if we go back to this 1985 paper, is that further down, Deutsch writes, one day it will become technologically possible to build quantum computers, and I admire that optimism, but he's not assuming, or rather he's assuming that we wouldn't use the same computing technology. Silicon by this stage had already become dominant. He says perhaps using flux quanta. So he is confident that we'll be able to build quantum computers, but he's already thinking it will require a different type of physical resource. And that's what we're going to talk about today. So some of the quantum computing technologies used today are shown here. We have, first of all, as Deutsch predicted, using the flux in superconducting circuits.
Sorry, I didn't know about Tony Leggett's role. It's a Leggett predicted.
Oh, I'm sorry.
Yeah, amazing.
Deutsch predicted, citing some papers, including Leggett's paper.
Leggett passed away last week.
Did he?
Yeah,
Ah,
unfortunately.
I'm sorry. I had not come across that news. Well, but he was certainly working with. I mean, it was probably Leggett that, because they were contemporaries, that would have told Deutsch about the use of flux quanta. And of course, that has gone on to become one of the dominant quantum computing technologies today, using these superconducting circuits to represent qubits. Another technology that's important is trapping ions, using the internal states of ions in traps. And if you want to simulate 1980s computer games using quantum systems, there's no better platform than these cold atoms trapped in using lasers, and they can be moved around. So there's already a very rich set of different physical platforms that are being used to develop early stage quantum computers. And with that in mind, we can ask the question, do we need another quantum computing platform? Why is there someone on stage saying, no, forget about all these other systems, there's a different way that I want to convince you is the right way to build quantum computers? Well, here are my arguments. First of all, that these existing systems have roadmaps that lead to extremely large machines. In order to be useful, not the demonstration machines that we have today, but to really solve the problems that got the pioneers of quantum computing excited, we're talking about vast warehouse-sized facilities connecting large numbers of dilution fridges, or you can see this requiring a large cryo plant there in that rendering from Chicago for these different systems. And the problem is that if these systems are reaching the scale of billions of dollars in cost per quantum computer, is this simply going to be too large and too expensive to justify its construction? And moreover, if these are vast billion-dollar facilities, it's going to severely, and countries maybe have one, that's going to severely limit the kind of applications that we can really use it for. And so what we want is a platform that's going to be able to scale to millions of physical qubits and beyond without exploding in cost and size. And of course, we already have technologies that can scale, not to millions, but billions of devices. I already showed this. This is an example of the M1 chip with 50 billion transistors.
I was told that our ordinary cell phone has about 1 billion.
Over?
The
Cell phone?
Has 1 billion transistors.
What? Probably even more than a billion. So what if there was a way to turn each one of these transistors into a qubit? Let's zoom in to what these transistors look like. Here's a cross-section of an example of these transistors. And we've got a source, a drain, a gate electrode, and it's about 50 nanometers wide. And of course, when it turns on, it draws a bunch of electrons underneath the channel of the transistor. But at low temperatures, by which I mean below 4 Kelvin, we can trap just a single electron underneath the gate of this transistor, and I'll show evidence of this later. So now we have a single quantum system, we can apply a magnetic field, and now the spin-up and spin-down states of this electron provide the qubit. So it's potentially, a potential route is to take these transistors that we can already put billions of, and use them to trap single electrons and use those as qubits. And if that's possible, then I would say we maybe don't need another platform, another physical system that's immature in order to develop quantum computers. Maybe we can use the existing computing platform, which is silicon, in order to develop quantum computers. And this is something which there's been much work in over the decades, starting with proposals from David DiVincenzo that I understand was here somewhat recently, and Daniel Loss in the late 90s, the idea of using these quantum dots, these trapped electrons, to represent information. And so there's been a lot of work over the past 20 years and more in realizing these systems in silicon. Here's a bunch of different examples going up to a few qubits using, let's say, bespoke processes in silicon germanium and silicon MOS. And so I would say the key challenges now to build on those kinds of small-scale demonstrations are how can we really use the scalable industry-grade fabrication that's used to make the chips in your mobile phones and laptops? How can we use those foundries to build qubits? How can we integrate those qubits with conventional electronics in order to build scalable systems? And ultimately, can we design actual QPUs that have come out of a foundry? And I think the other reason that's important for research, and you'll see this theme coming up several times, it's very expensive to develop foundries and make devices. All right? Universities spend vast amounts trying to do it, to set it up in capital cost and to run them. But there are foundries around the world that cost tens of billions to create, which anyone can access. And from a university, at particularly low cost. So most of these devices you'll see, they were designed by us, they were tested by us, but they were sent to be fabricated by a commercial foundry. And that dramatically reduces the cost, but it also dramatically increases the scope of what you can put on these chips.
Can I ask a theorist question?
Yes.
Maybe stupid, but what are the sort of decoherence times for these sort of?
So, the coherence times in the silicon systems can exceed milliseconds. So the coherence times are long for spins. Yeah.
As compared to say some other cold atom-based systems.
So compared to some of the trapped ions, they can be shorter, but actually what matters is the ratio of the clock speed to the coherence time. And actually one of the challenges that cold atoms and trapped ions have is that they have very high fidelities, but their clock speed is as much as 1,000 times slower. That matters because some of these calculations for molecular simulation, even on fast quantum computers, might take a month. And so if that's going to suddenly take 1,000 months, it's better be a very important problem. Good. So what I'm going to talk about today is how do we read out spins? How do I take a chip from a foundry and measure the spin of a single electron trapped under this gate? How can I build a complete quantum processor unit that I can program and simulate molecules? And then what else can I start? What other emergent physics can I see when measuring these CMOS chips? So first of all, I'll just introduce briefly the idea of a quantum dot, maybe familiar to many of you. We have confined an electron and in a region of space, and I can control the number of electrons in this quantum dot by controlling its potential. And this quantum dot is coupled to two reservoirs, and that's where the electrons come from and go to as I change its potential. As I change the potential, I will find that every now and then one of these levels lines up with the chemical potential of the lead, and at that point I can get electron transport through the quantum dot because electrons from the lead can enter and leave the dot. And this means I can build a single electron transistor. I can monitor the current through the dot, but that needs two terminals. And here's an example of a kind of measurement that one can make, and each spike where one sees enhanced current through the dot corresponds to the position of each one of these levels. So by counting the spikes, we can determine when the dot is empty and there are no electrons, and one by one, like sheep entering a field, we can count the electrons underneath the gate of this quantum dot. I can make the device even simpler by removing one of the leads, and then I'm simply monitoring whether an electron can tunnel on and off the quantum dot. That's called a single electron box. And that we can measure because there's a different capacitance. When an electron is able to respond to an AC field, there's a different capacitance than when it can't. And so we'll measure that change in capacitance. Will tell us when we've passed one of these transitions. Okay, so here's a chip that was made on a standard CMOS process, a 22 nanometer node, not super modern, maybe 6 years old at least. And on this chip, there are about 3 million transistors, not a lot by the standards of a mobile phone, a lot by the standards of a physics experiment. It has a serial programming interface, so we talk to it over a USB-style protocol and tell this chip what to do, while it's sitting at the bottom of a dilution refrigerator at less than a Kelvin. And so it combines digital and analog classical electronics with these quantum dots. And we're going to focus on this array here, in which we have designed over 1,000 addressable quantum dot devices, very similar to transistors. So each one of these has a gate, source, and drain. And as I mentioned, we can control when we want to monitor when electrons can tunnel on and off this quantum dot. So what we do is we connect the source to a tank circuit, which is an inductor and a capacitor, an LC tank circuit. And that tank circuit has some resonance that's shown here in blue. But when an electron can tunnel on and off, that changes the capacitance, that changes the tank circuit, it changes the reflected signal, and so we can monitor that in the change in amplitude of the reflected signal when we drive this with an RF. So here's some data. We'll just focus on this plot above. This is the reflected signal as I change the gate voltage on the quantum dot. I see nothing. Right now the dot is empty, and then I see one peak. Tells me now I've got one electron, and then another one, and tells me I've got two. So even with these quantum dots in CMOS integrated circuits, I can control one by one the number of electrons underneath this quantum dot. And I can do this on thousands, or in this case, over 1,000 different quantum dots. And because, yeah?
Sorry, again, here is messy.
Yeah?
So electrons are fermions, right?
Yeah.
So what does it mean to have two electrons?
Two electrons. So they're in orthogonal states. They're not occupying. So they will pair up in opposite spin states, but then you can just keep adding more electrons in different states.
There's some other degree of freedom in which they're orthogonal.
Yes, exactly.
Other than this.
Yes, exactly. Yeah. Good. And actually, yeah, we'll talk more about what happens with multiple electrons in a minute, because the spin matters a lot. Okay, and whereas it might take you an entire PhD to measure 1,000 quantum dots because you'd have to cool it down and warm it up one at a time, because these are all integrated on one chip, we could extract this diagram, this charging energy, from over 1,024 quantum dots in just 5 minutes, because we could address each one by one. This is what the chip looks like. It's very small. When you get them from the foundry, you get 100 different chips that are all the same, so it doesn't matter if you drop one. Even this isotopic enrichment that's beneficial to get longer coherence times, we like to use silicon-28. You can get those on 300 millimeter wafers, and then we put them onto printed circuit boards and wire them up, and then we might put them into one of our cryostats. This is an example of a cryostat that we've made ourselves. It slots inside a 19-inch rack. You can open it like you'd open your fridge in the kitchen, but this one goes down to 4 Kelvin, and you can see there's a lot of space that we can use to screw down these PCBs. And so with that, we then want to measure spin. And this means we need spin to charge conversion. We need something that's a bit more complicated than what I showed before. So now we have 2 quantum dots. One quantum dot is the sensor, and the other one is the one that we're going to call the qubit dot. And so we want to first correlate the spin of the qubit dot with its charge, and then the sensor dot is going to tell us if there has been a change in the charge state of the qubit Let's first understand this diagram. In this diagram, I've got two knobs. I can control the potential of the qubit, and here I can control the potential of the sensor. So in this direction, I have exactly the same I have exactly the same peaks that I had before. Each of these lines is the is the sensor dot changing its charge state. So let's focus on this line. This is the sensor dot changing from, say, n+1 electrons to n+2 electrons and so on. But now you can see these kinks. And these kinks represent a tiny shift in potential that occurs when the neighboring quantum dot, the qubit dot, changes its charge state. So although we are not directly connecting our tank circuit to the qubit dot, it's over here, it's isolated, it's being sensed by the sensor dot, and each time the qubit dot changes its charge, we see a discontinuity. So we can tell that the qubit dot is empty, and then that there's one electron after this kink, and then 2 and 3, and so on. So this allows us to have a sensor which is monitoring the qubit dot, and the region of interest is this one here. The sensor goes from n+1 to n+2. We actually don't really care how many electrons are in the sensor. We're just looking for this discontinuity. But the qubit dot is going from empty to having one electron. So what we can then do is we can, because we can control both of these voltages, we'll start in the position shown in red where the qubit dot is empty. And then we're going to pulse the voltage a few tens of millivolts, or less than a few millivolts, to the point where now the chemical potential of the qubit dot is below the Fermi energy. And so we're going to trap an electron. And that electron is going to get trapped in a random spin state. And then we're going to slowly bring up the chemical potential of the qubit dot. And at this point, where it lines up with the Fermi energy, two things will happen. Either, if it's spin up, the electron is going to tunnel off, and a new electron is going to come back onto the qubit dot in the down state. And then eventually, that electron will tunnel off. Or, if it was in the spin down state, it will stay there until the very end and it will tunnel off. So I have two different signatures. Either nothing will happen and the electron will stay until the end, or it will tunnel off and then a new one will tunnel on. And so this is now our sensor signal. What is the sensor picking up? The sensor is picking up that the qubit dot is empty and then it's full. And then sometimes it stays full and then empties at the end. But sometimes it's full, it briefly empties, is full again, and then goes back. And this is exactly the signature of a spin-up or a spin-down electron. And you can see this happens in about a millisecond. So this corresponds to a single shot readout of a single spin in a standard CMOS integrated circuit. So we can measure spins in these kinds of transistors. Yeah?
Determine the width of the tube?
Yeah, excellent. Yeah, that's the tunneling rate. So it's exactly the tunneling rate of the qubit dot. Actually, it's this arrow shown here, assuming that electron is going to the source.
Is that something you optimize for in your?
Yes, exactly, indeed. If the tunneling rate is too fast, then we need very sensitive measurement to pick up such a short blip. Of course, if it's too slow, it means we might need to take a second to see this.
So what sets the tunneling rate?
It's the geometry of how far that dot is away from the leads. Okay.
So that's something you can control.
That's exactly controlling the layout. When we draw the device, I mean, it's polygons. We draw, where our gate sits, where our other gate sits, and so on. Good. So that's at the stage of developing. So now we can read spins within standard silicon ICs. Now we want to take this technology and turn it into a fully functioning quantum computer. And so with this, we're still going to be using a 300 millimeter wafer process. It's a different one to the one I showed earlier. It's a bit more bespoke, but it's still an industrial foundry. And this is a picture of the outside of this device. It's a 4-qubit QPU, and it's the first one that was made where the chip was made using 300 millimeter wafer processing. In here, of course, you see the cryostat, you see all the control electronics hidden, and this was delivered to a third party. It's not in our lab anymore, unfortunately. It's in the UK's National Quantum Computing Centre. And in fact, on Monday, the UK Chancellor was meant to come to UCL to do an announcement, but then she realized that this machine was actually in the NQCC, and so she decided to do the announcement there instead. But let's have a look at what's going on inside. So to make a QPU, you need a few different ingredients. You need to read out the qubits. You need single and 2-qubit gates. So I want to focus on how we develop a scaled array of qubits. And for that, we need 2 different channels. We want an array of coupled qubits, and perpendicular to that, we need some sensors that can read their state. Now, the technique that I showed you earlier requires a high magnetic field. It's not so fast. So in order to read out our qubits, we use something called Pauli spin blockade, which measures the parity of 2 adjacent qubits. So this is now the new picture. We have a sensor like before, but now we have 2 qubits, and that we can move the electrons between those 2 quantum dots. The sensor can map the different transitions of those 2 qubit dots. And the transition we're interested in is one where there are 2 electrons, and they either can be equally shared between the 2 quantum dots, or we can tilt the potential so that both electrons go onto one dot. And this is the transition we're interested in, 1,1 to 2,0. And we're interested in that because that allows us to map spin information onto charge. And yeah, so what we can, the way that this works is when you have, when you're in the 0-2 state, when both electrons are on this right-hand dot, then the singlet is the ground state, and the triplet is an excited state. But when I move to an equal occupation, both electrons equally distributed on the 2 dots, then I have a full set of possible states, down, up, down, up, down, down, and so on. So what happens is when I start with the 2 electrons separate, I then tilt the potential so that the lower energy state becomes 0-2, but the electron only moves to the other dot if there's a projection onto the singlet state. In other words, if I have an odd parity state. So this is what a measurement might look like in time. If while the 2 electrons are separate, they're in a singlet state, and I tilt the potential, then they will immediately move over and give me the signal, the charge signal of 2,0. If, on the other hand, they're in up, up, or down, down, then when I tilt the potential, although the lower energy state is for the 2 electrons to be on one dot, that's blockaded because of the Pauli exclusion principle. So for several milliseconds, nothing happens, and eventually one of the spin flips randomly, and immediately my system projects onto a singlet, and I see a signal. So I have a very clear visibility between an even parity state, like T minus, or an odd parity state, like the singlet. And yeah, so that leads to a very high measurement fidelity, say 99.5% in just 10 microseconds. Single qubit gates, I can now read these 4 qubits by measuring their parity. I can perform single qubit gates by having a waveguide, a microwave waveguide that runs over the QPU, and that drives spin resonance, ESR, to coherently rotate the qubits. Here you can see evidence for each one where you find the spin resonance peak. Each one of these is the center of the spin resonance line. and then as you increase the duration of the drive, you have these Rabi oscillations that going up in the middle of these diagrams. So we can drive Rabi oscillations for each of the 4 qubits in the array. And then to do the 2 qubit gates, it's a little bit more complicated. I'm going to explain it for completeness. But it is using something called a geometric phase. To understand the geometric phase, we need to think about take a block sphere picture, but you need to look at the block sphere picture restricted to the odd parity subspace. So we're going to ignore the even parity states. We're going to consider a block sphere where the eigenstates are the spin eigenstates, up, down, and down, up. And that means that the states singlet and T0 and other combinations of these lie around the equator. Okay, so that's our picture. We're staying in this odd parity space. Now, we're going to imagine that we initialize our system out here, where actually we're far away from the position where the detuning of the two from the symmetry point between the 2 dots. And so in this case, the spin up and spin down states are good eigenstates. Which means if I want to think about this like a pseudo spin, then the effective magnetic field is vertically. So these are my 2 eigenstates. Now, as I change the gate voltage, I can change the splitting of these levels so that I go towards the singlet and T0 being eigenstates. And as I do this, I change the effective magnetic field so that the spins at this point have singlet and T0 as their eigenstates. And if I sit here, then I'm going to, the up-down state will evolve to down-up and so on. So what's happening here is a swap operation where the 2 spins are swapping their states back and forth because they're no longer eigenstates. And that already could be used as an entangling gate, a root swap. So doing that for half a period entangles the systems. But instead what I do is I sit at a point in the middle where the trajectory is mapped out here, and the solid angle of the trajectory gives me a phase. It's a geometric phase that is a controlled phase operation for the qubit. Bit technical, not super important. I suppose the key message is that we can perform one of the key universal 2 qubit gates, which is a controlled phase. And so now we have everything that we need to connect to one of the existing languages for describing quantum circuits, Circ, Qiskit, and so on. We can write some kind of a problem, some algorithm, send it to the computer. In this case, for example, we asked it to calculate the bond length of hydrogen using a variational quantum algorithm. Surprising, not so very surprising, but it predicted the bond length that we already know. But it's an example of being able to express a problem as a quantum circuit, send it to a real device, and get an answer. And of course, as we make these devices more complicated with large numbers of qubits, we can go to more complex molecules where we can't currently accurately calculate these values. Okay, so we can measure spins in CMOS devices. We can build fully functional QPUs from silicon. What else, what other physics can we start to explore from these CMOS integrated circuits? So the way we started this work is we wanted to think about scaling our measurement further. And let's say the secret that I didn't tell you is that you had this nice tiny chip with thousands of quantum dots, and we measured it using an LC resonator. But the inductor, the L in that LC resonator, was a superconducting inductor that sat off chip. And relatively speaking, it's very, very large. So we have thousands of quantum dots on this chip. Actually, we could fit millions. But they're dwarfed in comparison to the size of the inductor that we need for every qubit we want to measure. So this is very good to rapidly prototype, but it doesn't give you much scaling. Now, what we discovered a couple of years ago is that if you take the kind of CMOS chips that you have in your smartphone, etc., and cool them down. In addition to be able to charge, to load single electrons, you can also find materials that are superconducting. They're of course not there to be superconductors. They're there to match some work function, make a better transistor. But nevertheless, they are thin film superconductors that are present on silicon ICs. And so we found this material, the superconducting thin film. We measured its critical temperature at around 1 Kelvin. And so we realized we could start to make inductors out of this material. And we already had accrued evidence from these measurements of an incredibly dense kinetic inductance, which is a nanohenry per square. And why is that significant? Well, when you look at a chip, actually, if you think about when Apple announces its latest iPhone chip and you see a picture, pretty much the only thing that you can see with the naked eye are the inductors, right? These little coils, you can see one here, because they're the hardest thing to make small in integrated circuits. This one gives you an inductance of 200 nanohenries per millimeter squared. But with a superconductor, we can use the kinetic inductance from superconductors to make inductances as much as 7 nanohenries per micron square. So the potential of 35,000 greater inductance density. So that's what we did. We took these devices with what we believe are titanium nitride thin films, and we made a tank circuit out of them. And we showed that we could get resonance when we cool down below into the superconducting state. And that, moreover, we have now a tunable inductance. As you often get when you have a kinetic inductance, we could tune it by temperature, we could tune it by magnetic field, we could tune it by the DC current through the inductor, and even by the RF current through the inductor. So, out of the box, in a standard CMOS process, we have a 35,000 increase in inductance density, and we have all of these different knobs to tune it. And now what it means, we can connect it to a quantum dot and use it as the LC circuit for sensing. So these are the same kind of charge stability diagrams that I showed before, but now they're being measured entirely on chip. The inductance, the LC tank circuit, is on the same chip as the quantum dots, and it's almost 100,000 times smaller. This is the peak, one of these Coulomb blockade peaks where we can see electrons tunneling on and off. And now, with just 4 nanoseconds of integration, you can very clearly separate those two signals. So you have a huge increase in the charge readout fidelity. And you can also start to see the nonlinear regime for this superconductor as you start to drive it more and more strongly. And actually, just as is used in superconducting parametric amplifiers, this nonlinear regime gives you a further sensitivity boost. So with these numbers, we get a charge readout time, extrapolating based on the SNR, means we would get an SNR of 1 within just 1 picosecond of integration. So in addition to being much more scalable and dense, we have a potential for much faster, higher fidelity readout. And actually, there are much broader applications. As I said, whenever circuit designers are trying to design inductors, they have to resort to these very large systems. This allows you to increase their density. Kinetic inductance detectors are used in astronomy because they can detect particles. Now, what we're saying is that we can take existing CMOS ICs and you could put millions of these inductors. So you could use these to make new types of astronomy detectors.
What's causing the superconductivity in this?
Well, we think it's titanium nitride, thin films.
Okay, so that goes superconducting.
Yes, yes.
Ordinary S wave and all that.
We think, yeah, we think so.
Yeah, you think
Yeah. And so, yeah, so this could be used for those sorts of detectors. And of course, the wonderful thing is you can then automatically integrate the digital and analog electronics to measure them. And also, people have begun using coupled arrays of nonlinear superconducting systems to perform quantum simulation. And again, here, just because of the sheer scale, you could couple vast numbers of these resonators.
Quantized vortices of superconductors are not playing any role here.
Sorry?
Quantized vortices of superconductors are not playing any role in these superconductors.
Quantized vertices. I mean, there's a magnetic tunability in the kinetic inductance. So,
Like in squid.
like in squid, no, not quantized vortices. I mean, they're definitely vortices. The presence of vortices is the reason you're able to tune the kinetic inductance. So by applying a magnetic field, you can adjust that. But it's not a squid loop. It's a superconducting wire from a very thin film, so that you get a very large kinetic inductance. So yeah, cryoelectronics, astronomy, and quantum simulation are three applications of this kind of thing. And as I said at the beginning, I think the really powerful thing is that anyone can access this. Right? You can any electrical engineering department is likely using this kind of process to make integrated circuits. These chips can now, if they're cooled down with the right design, be used to explore these sorts of phenomena. So I'll attempt to answer the question I set out at the beginning of my talk. Could modern CMOS ICs provide a complete platform for quantum computing? Well, first of all, we can measure over 1,000 quantum dots, including measuring their spin that's come out of a standard CMOS IC. We can build complete quantum processor units up to 4 qubits so far using these single and 2 qubit gates. And we can incorporate that into a full stack quantum computing system that someone with no knowledge of silicon quantum dots can use because they're just running with these standard protocols. And then we have these superconducting elements that can be accessed within modern CMOS ICs to create compact superinductors. And of course, what I didn't talk about is all of the other cryo CMOS components that you can build, low noise amplifiers, obviously other electronics which uses CMOS. So first of all, this was a big team effort. I've highlighted a number of the different PhD students along the way: Constance, Isabel, Clark, Jacob, Mark, Gork. In fact, almost the entire first row here are PhD students. And rest other staff and researchers at Quantum Motion that contributed to the specific results I showed here. And yeah, so David Joyd said one day it will become technologically possible to build quantum computers, and maybe using flux quanta or maybe using silicon integrated circuits. So thanks very much for your attention.
So what are your current bottlenecks to scale it beyond 2 qubits?
So I would say at the moment one of the bottlenecks, larger ones are being tuned up right now, and one of the bottlenecks is in the tune-up of getting one electron into each of these different quantum dots and tuning the tunnel couplings between each of these to get all of these different gates. So it's, I would say one of the main ones in the short term is a tuning bottleneck, which we're addressing using automated tuning routines. The 4-qubit system was largely tuned up by researchers manually. Now we're already using an automated tuning routine to take this array of 16 quantum dots and put them all in the right charge state. But it's this kind of complex process that is essential in order to go to larger numbers. Because
each qubit takes its own tuning.
yeah, each qubit, and it needs tuning for its own state, but also to control to tune the coupling. And the automatic tuning from the computer, the evidence is that it does it slightly better than the human, both faster, and it finds a more optimum state. But the biggest advantage is that the computer is much better at doing 16 of these in parallel than in person.
I saw the spin readout times are in few milliseconds.
This indeed, in this device where I was not using a parity readout, was quite slow. But when we used Pauli spin blockade, the readout time was much faster. So there we were able to achieve 99.4 5% fidelity. So yes, you're referring to the time scale here, right? But you don't need to wait 2 milliseconds. Okay, so the goal is to distinguish between the green and the blue signal. You don't need to wait 2 milliseconds to distinguish them, right? With this SNR, we know already within a few microseconds that the signal level is here and not here. So the readout time in this experiment for 99.5% fidelity was just 10 microseconds. And with the new superinductors that I showed at the very end, we think we can bring that time less than a microsecond. So we are already doing mid-circuit readout of these systems, which is maybe where your question was going next.
Correct. Daniel Larson, David, they use nuclear spins in a fundamental way. Coupling nuclear spin and taking advantage of that. Nuclear spins are very weakly coupled to the environment and so on.
Did they?
Or is it a different work?
They were prolific when it comes to different schemes. So in this one, they had something a little bit crazy with these ferromagnetic things, and yeah, but the basic idea, we don't use this part of their proposal, but we use the idea that we have quantum dots and we use their spin. I don't think they were using nuclear spin. It's not what we try to get rid of all the nuclear spins. Silicon already is nearly nuclear spin free, so only 5% of silicon is silicon-29. But then we deplete that down to a few hundred ppm in order to get longer coherence times.
These geometries are all still going to be two-dimensional. And in a lot of the quantum computing, they're pretending that they can talk, any qubit can talk to any other qubit. How is that going to actually pan out?
I love this question. All right, let me see if I can give you. It's not here. Okay, I will attempt to do justice to this. So we have. We're not thinking all to all, but our architecture for scaling to utility scale, it uses a version of the surface code. A surface code is this two-dimensional, it relies on sort of nearest neighbor coupling, and so it's very natural for these kind of 2D systems. But our implementation of the surface code actually builds a number of different stacks of 2D surface codes. And I can explain a little bit after how we implement that, but it's within, in the end, it's extensions of these bilinear arrays. And so what we don't have is a single 2D code. We have what's called a stacked surface code. And we also have a very natural way to create logical operations, these transversal gates between stacks. So even though it's a 2D chip, our quantum error correction code is 3D. And this is really powerful because it means that then if you want to do gates between logical qubits, you don't have to move them out of the way. What you do is you move them up into one of these intermediate layers, and then they can perform their logical qubit gate and move back down. So yeah, it's not something we can talk about it later, but it's a stacked surface code. And in fact, you can even, theorists dream up these crazy things, like there's this thing called a folded surface code. So someone realized that one of the challenges with the surface code was that the ends are either X-type or Z-type. Sorry, this will mean things to some of the audience, but not very much. And so they realized, well, if we just folded the chip down along the diagonal, then you would solve this problem, right? Then the edges would have X and Z-type character. But who on earth thought that I was going to take a chip and fold it along the diagonal? But actually, with the implementation of this that we have with this stacked surface code in the computational space, we can do exactly this and fold our logically we can fold our chip along the diagonal, so we don't have to start cutting it. And so it's a powerful platform for implementing these kind of more complex types of surface code.
No, actually, I will ask the exact same question.
All right. Okay.
Any more questions? I had a question. So one of the requirements requirements of fault tolerance is like constant supply of fresh ancilla qubits. So I don't think you have a constant supply. Like it's not a free resource. So like, what's the reset time of your qubits, and how much circuit depth can you do?
Yeah. So the reset time here is the read time, and each time what we're very good at is so when we tilt our potential, we do everything looking at parity, right? So we tilt two electrons so that they tunnel onto the same dot, and at that point we've created a singlet quite quickly, and then we separate them. And so that is the process by which we are continually refreshing ancillas, and that's what we think, what we currently do on the sort of 10 microsecond time scale, and we think we can do on the sub-microsecond time scale. And that's, as you rightly point out, that kind of, each of those different elements, initialization, the gates, and the readout, they represent the most important clock cycle for a fault-tolerant quantum computer, which is the code, one complete cycle for this surface code, and that's what we target getting to the level, the whole cycle, for a few microseconds.
Yeah, and what's the crosstalk between qubits? And do you see some non-Markovian errors or something?
Yeah. So crosstalk is something that we're still working on. I think the interesting thing with crosstalk is that in this regime of NISQ machines, we want to be able to control what every qubit is doing. As we move towards fault tolerance, we are asking most qubits to do exactly the same thing, right? They're either all doing a Hadamard or not. And so the problem of crosstalk becomes very different. We can individually address all of those 4 qubits in our NISQ type QPU, and we are scaling up to larger QPUs. And we certainly see the crosstalk that when you try to drive one, other qubits that have a similar frequency respond a bit. But I should say that we measure fidelities in excess of 99%, and that is measuring parity. So that 99% fidelity includes unintentional driving of a neighbor. So it's not like one of these ones where I'm doing randomized benchmarking, I'm only focused on one qubit, and I could be screwing up all the others. So that tells us that the crosstalk is at least not too bad. But the reason I'm less worried about it is as we go towards fault tolerance implementations, we're trying to drive all the qubits.
Can you do quantum simulations in your quantum computer, like Hubbard model?
So
One of the challenges.
yeah. So today, the largest computation we've done is this simulation of the hydrogen molecule. So that's currently that's a trivial problem, and so I would say with silicon it's not yet at the stage that it's doing Hubbard. But I would use your question to advertise a couple of results from Phasecraft, which has been doing Hubbard model on Fermi Hubbard model on 2 quantum computers, on Google and Quantinuum, and those I think are now going beyond what can be achieved classically. So it's showing Fermi Hubbard is then being used to demonstrate quantum advantage on these existing machines.
What dimensions?
Those 6 by 6. Time dynamics.
Oh, time dynamics.
Yeah. If you think you can, I mean, I think every time anyone puts out a quantum advantage paper, it's a red rag, right? Because immediately you get people saying, I found a way to do that. Because the quantum advantage result is I found a way to do something on a quantum computer which is better than any other method on the planet. And of course, so I think Ashley Montanaro, the CEO and co-founder of Phasecraft, has these different definitions of quantum advantage. And it's just defined in how long does it take for someone to refute the result, right? if it takes a day, if an archive paper appears the next day saying, look, I can do this better, you know, that's the sort of worst type of quantum advantage. You know, if it takes a week or a month, if it takes a PhD student 6 months of focused effort to outperform the method, you know, that's already a type of quantum advantage. And so, you know, we have to calibrate things differently. But I think those results have been on the archive already a few months, and I've not seen a complete takedown, but maybe some people are working on it.
I would like to request Professor Santosh to present a memento
Oh.
of thanks.
Oh, thank you very much. Thank you. Thank you. Thanks very much.